Hello everyone and welcome back to another video of this Numpy course. So till now we have seen a lot of things in Numpy library, and today in this video we will look at specifically how you can use Numpy to do things like generate random numbers and do things like linear algebra, and we'll also see some statistical methods in NumPy, statistical methods like mean, max, variance, standard deviation, percentiles, and like that. So a basic prerequisite for this today's video will be that you should know basic things about linear algebra. High school level linear algebra is enough, and some descriptive statistical knowledge is also required for this video. And we'll see how to generate distributions in statistics that we'll cover in this random number generation. So you should have some idea of statistical distributions as well, like normal distribution, uniform distribution, and exponential distributions. So basic distributions that you see in statistics, you should know them. So this is the objective for today's video. Now I will go to my notebook and I will import the NumPy library, import NumPy as NP. I will run this. So we'll begin with random number generation. So we will use this submodule called np.random. So we can do a lot of things using this, like we can generate random numbers uh, from different distributions like the uniform distribution, normal distribution, exponential distribution, binomial distribution, and many more. We will see few of them today, and we can do some random shuffling in our data. Like we can use um, permutation method. Sorry, permutation, shuffle. So these will help us to rearrange the data in our array randomly. So this is also very useful. Then we have this method called choice that helps us to I should say sample the data randomly. Okay, so these are the things that we will cover in this random number generation topic. So let us start by first I will create an array. So I will name it A and I will write np dot arrange say 7, and I will write the shape okay yeah, np dot arrange 7, and I would like to print this. So this is our array A. Now I would like to shuffle the data in this array randomly. Okay, so for that I will write np dot random dot permutation, and I will pass this array. So what I get here is the data that you see here is randomly shuffled. The data in A is still the same. So the A is still the same, but what this function has done is it has randomly rearranged the data inside it. So this is a very useful thing to know because in data science we often come across the thing like sampling the data and random splitting and all that. So this can be a very useful thing to know. Okay. We also have another function called np dot random dot shuffle. So this will also do the same thing, but this time we don't get any output. Actually, what has happened is the array A is shuffled in place. So the array A is changed. The data is rearranged randomly. The data is still the same. We have same values, but the arrangement has been shuffled, you can say, randomly. Okay, fine. Now we'll come to see some distributions that you see in statistics. So first we'll start with this normal distribution. So for that we'll write np dot random dot and the name of the distribution. So first I will write normal distribution, so normal, and inside this I will give the parameter of the distribution. So if you know about the statistical distributions, so you should know that a normal distribution has basically two parameters, that is the mean and the variance of the distribution. So I will write the mean, I would say LOC, this is the mean. I want a distribution with mean 2 and I guess the standard deviation say 1, and then we'll pass the size of this of the data. We can actually pass the shape of this array that we want. For now I only want a array of 10 values. Okay, so here I have, so these are the values that are generated from a normal distribution. Fine. So I will write np dot random dot normal, and I will pass, first I will pass the mean and the standard deviation, and then I'll pass the size. So here comes the mean, the standard deviation, and the size. So a normal distribution looks something uh, like this. So here we have the mean, and the distribution, the spread of this distribution is sigma. Fine. Okay. We also have this standard normal distribution. So for that I will write np dot random dot standard normal. Now in this you don't have to pass the mean and sigma value, because a standard normal means distribution, normal distribution with mean 0 and variance 1. Okay, so simply you will have to pass the shape of the array that you want. Say I want 4 cross 3. So here I have. Fine. We also have some more distributions. Now we have, say for example, the uniform distribution, np dot random dot uniform, and for that we have two parameters, the a and b. So first we have the low value, that is a value, that is say from 0 to 1. So from 0 to 1 I want a uniform distribution from 0 to 1. And how many points do I want? So for that I have to specify the size as, say for example, I want 5 points. np dot random dot uniform. Okay, I have a spelling mistake here. Okay, actually I forgot to show you here. Okay, say this is array b, and I have generated this b. So each time I generate, each time I run this, I will get different values, because this is a random data generation method. Okay, so for example, I have this array b. Now if I have to if I have to check the mean and the standard deviation for this, I should be getting around 2, because I have passed here 2 as the mean. So approximately around 2. You can see it's not exactly 2, but if I increase the size of the data, say I want to generate 100 points, and now if I, okay, let's not print this, it would be a big array. Now if I write this b dot mean, you can see it's very much closer to the parameter 2. Okay, and same way we can verify the standard deviation by writing b dot std. So it's around 1, very close to 1. Okay, so this way you can use these methods dot mean and dot standard deviation to get the mean and standard deviation of the array that you are trying on. So here in this case it's the array b. So not only for this normal distribution, you can do it for any data you want. Say for example, this was our array a. I would write a dot mean to get the mean value of this array. Okay, so this way you can verify that the distribution is actually following our parameters that we are passing. So we were here at the uniform distribution. So these are the values from a uniform distribution. If I have to show you here, so np dot random dot uniform. So we have this low value, high value, and the size. So for example, a uniform distribution looks something like this. So something like this. This is say low, this is high. So from low to high, we have values that are uniformly distributed. So each of the value is equally likely to be picked. So this is what a uniform distribution means. Okay, so for example, I want from 1 to 3, I want 10 values. So this should give me a 1D array which has 10 values, and the data is uniformly distributed. Actually, it would not be perfectly the same, because this is a random generation, and if the size is very high, then we would actually get a distribution that is very close to the uniform distribution. We have actually seen this phenomena here when we calculated the mean value um, after generating 100 points. It was very close. So this is actually called in statistics, we call this weak law of large numbers. So it says that the more data size we have, uh, the more accurate our statistics will be. The calculated statistics will go closer and closer to the actual value if the sample size is large. So this is what weak law of large number means. Fine. Now we can further explore more distributions like np dot random dot binomial. So if you know binomial distribution, it has two parameters. First is n. So say I want n is equals to 10. Actually, this is not the size, it's the parameter of this distribution. So n is equals to 10 and p, which is the probability of success, say I want 0.3. So p should be between 0 and 1 because it's a probability. And size I will pass, say I want 10 points. So it will generate 10 data points, which are from a binomial distribution with parameters n equals to 10 and p equals to 0.3. So further we can explore np dot random dot exponential. So here we have to pass the scale and we have to write, say I'm going to write 1 by 3. Now why I'm writing this 1 by 3? Scale is actually the parameter of exponential distribution, okay? Now 1 by 3 is actually, this 3 is actually the lambda value of exponential distribution that we see in statistics. So I think it has formula like, so the exponential distribution will have formula like, I think lambda e to the power minus lambda x. So on this number line, this is x. This is actually the value of the random variable, and the PDF basically looks something like this. So roughly like this. I should draw, yeah, something like this. Okay, and then we have to pass the size. Say this time I want to generate a 2 cross 3 array. So we have the exponential distribution. We can actually plot this and visualize this. So for this, I will import matplotlib dot pyplot as plt. Okay, let us sorry, plt, and I will write plt dot hist, and say first I will create a distribution. Say d is equals to, say I want to create a exponential distribution with lambda equals to 3, and I want a 1D array. Say I want 100 values, and I will simply plot the histogram of this and visualize this. So roughly like what I have shown you previously on the board. So more is this size here of the data, the closer your distribution will be to the actual distribution. So if I say 1000 points, it looks more prettier than before. Say if I had only 10 points, then it's very different from the exponential distribution. It doesn't look like an exponential distribution really. Say 10,000 points. So this would be much, much closer to the actual distribution. Bins is equals to say 15. So it's like we have more bins. If I say 20, and I don't want this output here, I will write plt.show. So this is more, we can say, granular, more detailed graph because we have more bins here. So yeah. Okay, I think till now we have completed this random number generation. Actually, there is one more thing left I have to show you. We have this function called np.random.choice. So in this, first we pass an array. Say I want -1, 1, 0, 2. Okay, so this is an array, and I want to sample the data from this array, and I want say 20 points. Okay, so what this function does is we give a data array, and from this data array we randomly sample points from this array. Now this has only 4 values and I want 20 values. So this is actually called as bootstrap sampling. Bootstrap sampling. Uh, yeah, bootstrap sampling. So it's like tossing a dice. Uh, and okay, first let me run this. So we have 20 values and they are randomly sampled from this data. So to explain you more clearly, I will write, say the dice values 1, 2, 3, 4, 5, 6. So imagine that this data is our dice. It has 6 values and I'm rolling this dice 20 times and noting the outcome. So this is same as doing this computer simulation. Okay. So this random dot choice is actually does uniform random sampling. So each of the values in this data is equally likely. Okay. So if we say I write d is equals to this, and I want to generate 200, say 2000 such samples. So 2000 dice rolls. And if I plot this, the histogram of this data, I write pins is equals to say 20. Now I should get something like this. Yeah, so this is actually uniform distribution, right? So each of the values is almost they have equal occurrence. You can see here. So more is the size. I already told you. More equally spread, these values will be 1, 2, 3, 4, 5, 6. So they are much well distributed uniformly. Okay. So it doesn't matter what the size of the data is. Say for -1 and 1, I want 20,000 samples. So it doesn't matter what is the size of the data. Uh, sorry, -1 and 1. So I have -1 and 1 values. You can see they are almost equal. Okay. So this is what random dot choice does. This is actually sampling, and this is very useful. A useful thing to know. You will see in future that this comes a lot help to us while sampling the data. There is also one more thing we can do with this, say 0, 1, 2. So I have added some more data to this, say 4, 5, 4, 3. Okay. So we have added some more data to this, and this time I only want 3 samples. So, and I don't want to plot this, I will just print the data. So I have generated 3 values. Let's run again this. Now, you know that this is the data and I only want 3 values from this, but I don't want values to be repeated. And you can see that in this sample, this value 1 is repeated. So I can set replace is equals to false. So by doing this, I'm telling that each value is selected only once. And if I write 10, say I want 10 values from this, but actually the size of this data is only 6 values and I want 10 values with replace equals to false. So this throws an error because this is not possible when replace is false. Because for 10 values to be selected, we want sampling with replacement. Okay. So this is called sampling with replacement. Fine. So with that, we have completed random number generation. Now we will move on to the topic of linear algebra. Um, if you know some basic linear algebra, then you know we have vectors like this. Say I have one vector, sorry, yeah, say one vector, uh, this vector. So I will call this 3 comma 2, and another vector, say, yeah, this is, I should say, um, 1 comma 4. So this is x axis, this is y axis, and we have these two vectors. Sorry for the drawing. So 1 comma 4 and 3 comma 2. So these are two vectors. I can create these two vectors in Numpy using this 1D array. Actually, the vectors in Numpy are 1D Numpy arrays. 1D Numpy arrays. So let us try to create these two vectors, 1 comma 4 and 3 comma 2. So yeah, let us create, say v1 is equals to np dot array, and first is 1 comma 4, and let me copy it down, and I will write v2 is equals to 3 comma 2. So these are the vectors v1 and v2. Now I want to add these vectors. We know it will do the addition element wise. So this is the mathematical addition of two vectors. Corresponding elements will be added. We have already seen this in previous videos. So the result should be 4 comma 6. So I will write another vector 4 comma 6. So somewhere around here. Yeah. 4 comma 6. Okay. So this is the mathematical linear algebra that we can do in NumPy as well. So remember that the vectors in NumPy are just 1D NumPy arrays. We represent them using this 1D NumPy array. Okay, fine. Now let me introduce you to this module called np dot. And yeah, for the matrix we have 2D NumPy arrays. So for example, matrix M1 is equals to np dot arrange 12 and 4 comma 3. So I have to reshape 4 comma 3, and I would like to print this. So this 2D NumPy array is called matrix in linear algebra. That is what I wanted to show you. Fine. Now using np dot lin alg. So using this we can do linear algebra stuffs like matrix rank, inverse, eigenvalues, decomposition, and a lot of other things using this submodule called lin alg. So it basically means linear algebra. Okay. So first I will write np dot lin alg dot norm. Norm basically calculates the vector length of a vector. So for example, I want to calculate for v1. So this is the vector length for v1. Actually, this is Euclidean norm. So I can do this other way also, like np dot square, sorry, np dot power v1 2. So what I'm doing this, I am raising the values in v1 to 2, 1 square, 4 square, and I will add this. So I will write np dot. So I will write just dot sum. And after adding this, I will put a square root on this. Sorry, dot sum. After this, I will put a square root. So np dot sqrt. So these two values are same. So what np dot linear algebra dot norm does is np dot linear algebra dot norm. Say for example, I have this vector v1 as v, say this vector v as v1, v2, v2, v3. Okay. So this norm will calculate the vector length, and we know that it is the sum of the values v1 square plus v2 square plus v3 squares and the square root of this. So this is the formula for vector length. Now we come to dot product. We can do dot product in NumPy, writing np dot dot, and I want dot product between v1 and v2. So dot product, if you know in linear algebra, is first we will multiply the values correspondingly. So 3 into 1, 3 plus 4 into 2, 8. So 8 plus 3 would be 11, and that is nothing but the dot product of v1 and v2. So similarly, we can also do, okay, let me come here, and I will create a matrix, second matrix M2, and this will be, let me copy this, and this matrix will be 3 cross 4, and I would like to print this. Now I have M1 and M2. Let me print M1 also. So this is M1 and this is M2. So M1 is 4 cross 3 and M2 is 3 cross 4. So I can multiply these two matrix. I can do M2 at the rate M1. This means I want to multiply these two matrix in this order, M2, M1. So order, we know in matrix multiplication order matters. So M2, M1 is possible because M2 is 3 cross 4 and M1 is 4 cross 3. So the resulting matrix should be 3 cross 3. So I can do M1 and M2 also. Here it is possible to do, but it may not be possible sometimes. So M1 and M2. So the resulting matrix will be 4 cross 4. Fine. We can also generate some matrix in linear algebra using, say, np dot zeros 3 comma 2. Sorry, np dot zeros. Sorry. So this is a 3 cross 2 matrix with all the values 0. So this is, we know, 0 matrix in linear algebra. We also have identity matrix, and we can do np dot I, and I'll just pass the number, say, 4. So this is a square matrix 4 cross 4, and it's identity matrix. Okay. And we also have np dot diagonal, and I will pass this list 1, 2, 3. And what I will get is the diagonal values, same as the values that I passed in this list. This works in different way also. For example, I have matrix M1, and if I write np dot diagonal M1, so this time it's a matrix, not a simple 1D array. So what I should get here is this will give me the diagonal values. Diagonal values are the positions, like, for example, this is a diagonal element because the index of this is 0 comma 0. This is a diagonal element because it has index 1 comma 1. Similarly, this has index 3 comma 3. So 0 0 1 1, sorry, this has, I think, 2 cos 2. Yeah, 2 cross 2, 2 comma 2, the index of this value. So these are the three diagonal values in this matrix. Note that this 11 is not a diagonal value because it's 3 comma it's 4 comma 3. Yeah, so this is not a diagonal value. Fine. Let us try to run this. So these are the diagonal values that I get. Now we can also find the rank of a matrix by writing np dot lineage dot matrix rank. So I will pass this matrix M1. So the rank of this matrix M1 is 2. This basically means that the number of linearly independent columns or the rows in this matrix are 2. To better understand this matrix rank concept, you should know some linear algebra. I already told that at the starting of this video. Okay, we can do the inverse of the matrix by writing np dot lineage dot inv and pass the matrix. It says it must be a square matrix. So if I write PINV, so this is called the pseudo inverse of matrix M, because we know that inverse in linear algebra is possible only for the square matrix. So M1 is not a square matrix. So we have to use this PINV. PINV is basically the pseudo inverse. Okay, which is possible for any matrix, square or not, it doesn't matter. Okay. Next, we have this eigen decomposition. We can do using np.lineage.eig and M1. So eigen decomposition is only possible for square matrix. So let me create a square matrix S, np dot random dot normal 0 1 9 dot reshape. So you should know by now what I am doing. All this. So this generates random number from normal distribution. It means 0, sigma 1, and I want 9 values, and I want to reshape it as 3 cross 3. Then I will find the eigenvalues and vectors for this. So it actually gives two things. So I should write evals, evex. Evals are basically the eigenvalues of this matrix S. So this is a 3 cross 3 matrix. I have 3 eigenvalues. Evex are basically the eigenvectors. So I have 3 eigenvectors of this matrix. Note that the eigenvectors are column aligned. So this matrix that you see here, actually it's a 3 cross 3 matrix, and it has eigenvalues aligned in this way. So this is the first eigenvalue. This is the, sorry, eigenvector. This is the second eigenvector, and this is the third eigenvector. Okay, fine. Then we can also find the determinant of a matrix. So if I write np dot linalg dot determinant S, so this is the determinant of this matrix S, and note that determinant is also possible for, is only possible for square matrices. Okay, so we have completed this linear algebra topic, and now we'll move on to some statistical methods in NumPy. So you should be aware of some basic statistics, descriptive statistics like the min, max, the mean, median, variance, standard deviation, percentile, quantile. So let us try to implement this in NumPy. First, I will create a uh, data array, say np dot uh, this time uniform, np dot uniform from 3 to 7. I want uh, say I want 20 values. Okay, let me give you the shape, that is 5 comma 2, and I will print the x. Okay, sorry, I have to use this random dot random. So this is our data array x. This is a 2D array. Fine. Now let me use the statistical methods one by one. So first is x dot sum. This will return me the total of all the values in this array. If I want to find the sum of each column, so not full array but each column, so I would write x is equals to 0. X is equals to 0 means that for each column it will calculate the sum separately. So you know I have two columns in this, so I get two values each for one column. So the sum of the first column is this, the sum of second column is this. Similarly, I can do for rows as well. So by passing axis is equals to 1, this will calculate the sum for each row. So 3.92 plus 6.74. So the sum of first row is 10.67. So similarly, we have I think 5 rows in this matrix. Fine. Now we see npx dot min. From name, it should be clear. It should return the minimum value in this array. So this is the minimum value in this array. If I do x dot max, this is the largest value in this array. I can do x dot median. Okay, it has no attribute median. I think I have to use median from this np dot attribute, sorry, method, np dot median and x. So median basically is the point that divides the data into two halves. So the interpretation of this value is that 50% of the values in our data array x is larger than 4.01 and the rest 50% is smaller than 4.01. So this is the definition of median, sorry. Similarly, we have some more methods like x dot var. This is the variance of the matrix x. If I do x dot std, this is the standard deviation of x, which is nothing but the square root of this variance. You can actually verify it in your notebook also. Uh, I suggest you that you open a notebook and do these things with me. You can use this axis is equals to 0, axis is equals to 1, these methods as well. I'm not showing here. Okay. Then we have this method called argmin. This is basically returning me the position of the minimum value. By the way, what's the minimum value? It's 3.22, and 3.22 I think I can find here, this position. So I have to count 0, 1, 2, 3, 4, 5, 6, 7 like this. If I want to calculate the position of minimum values for each row. So for example, in the first row, I have minimum value 3.92 and its position is this 0. In the second row, this is 4.02. This is the minimum value and its position is 1. So for each row, I want to return 0 and 1 uh, based on what is the position of the minimum value. So x dot argmin, and for each row, I will write x is equals to 0. Sorry, x is equals to 1. Yeah. So in the first row, in the 0th position, I have the minimum value. In the second row, in this position. So similarly like this. For each column, I can write this. So in the first column, in the third index I have the minimum value, and in the second column also in the third index I have the minimum value. So for this column I have this minimum value, for this column I have this minimum value. So the position. So similarly x dot argmax, and x is equals to 1. Argmax, you know what it does? The position of maximum value. This is also a very useful methods, argmin and argmax. So you should note this. Uh, Something more, we have x dot cum sum. Actually, I should write. So let us try this on some only on one array. So I shall write. Let me select just this first column in this array. So which is this, and if I do np dot cum sum or cum sum. So first let me print this. Okay, then I will do this. So this is the first column, and if I write np dot cum sum of this first column, see the first value is the same. The second value is actually the sum of all the values on this position and behind this. So this is actually the sum of this value and this value. The next value is the sum of all the values that are behind this and this 4. Okay. So similarly, this value is the sum of all the values behind this. Okay. So you can also do like this value will be the sum of this previous value in cum sum and this value. Like that you can also interpret this. So like cum sum, we also have this cum prod. By the name it should be clear. So it will do cumulative product. So this time say I'm selecting this. Okay, let it be this column. Okay, this is cumulative product. So first value is the same, second value is the product of these two values, third value is the product of all these values, fourth all these values, like that. So this is a large number. Yeah, because we this time this is cumulative product. So yeah. And yeah, one more thing in the end, which is also very important, we have np dot percentile, and if I write, so it will calculate the percentile value that we give. For example, let me create x is equals to np dot random dot standard normal size is equals to 10, and I would like to print this. So this is our array x. If I write np dot percentile, and I will pass this array, and here I will provide the percentile value that I want. Say I want the 10th percentile. So this is the 10th percentile value. The interpretation is that the 10% of values are below this value and 90% are above these values. Okay. For example, I write here 98. So this is the value in which 98% of the values are equal to this or less than this. Okay, so 98% values are below this value, and only 2% of values are above this value. So this is the interpretation of percentile. We can pass multiple percentile values if you want. Say I want 98th percentile, I want 10th percentile as well, I want say 50th percentile. It's better if we write it in increasing order, although it's not necessary. Say 99 percentile. So the 10th percentile value is this is the 50th percentile value, and this is the 99th percentile value. We can verify that this 50th percentile is also called the median of the array x. Yeah, so this is the median of x, the 50th percentile. We also have this similar function called np dot quantile. Here also we provide this array x and the percentile, but this time we don't provide the percentile from 0 to 100. So percentile is here in this we have 0 to 100, but here the percentile we provide as between 0 to 1 basically. So for example, the 10th percentile should be 0.10, 50th percentile should be 0.50, 99th percentile should be 0.99, 5th percentile should be 0.05. So you have to divide the percentile by 100 and you will provide this in quantile. So yeah, similar thing, but the percentile value scale that we provide is different. So here we divide by 100 and give the values. So I think I have covered almost enough of linear algebra, random number generation, and statistical methods in Numpy. These are the things that you will see a lot while using NumPy in data science and machine learning applications. Okay, so yeah, that's it for today's video. Uh, we have made it to the end of this video. I hope you are enjoying this playlist. So I think this is the second last video of this playlist, and in the last video, we will see some application of NumPy in some real life scenario questions. Okay, so till now we have only seen what NumPy has, what you can do, all the methods, attributes that you see in NumPy, and how to use them. Okay, we'll see some application questions, and we'll try to figure out in the video how we can solve it using the NumPy library. So thank you for watching this. I will see you in the next video.